Hi everyone. In the last episode, we discovered the important notion of binomial coefficients. Let's recall what they are. We counted the number of ways to choose an unordered set of k friends to invite from our total list of n friends. Generally, we would like to choose k objects in no particular order from a list, from a set of n objects. We computed this, and the number was the number of ways to do that. The number of all possible invitation lists is n factorial divided by k factorial, and further divided by n minus k factorial. This is an important notion that comes about in many areas of mathematics, and it is called the binomial coefficient, denoted n choose k. Binomial coefficient. I know you guys are eager to go back to probability questions, but we will need to spend this and the next episode to practice with binomial coefficients. They're so beautiful, and you will have fun just doing that. Then we'll get stronger and go back to probability. What do you think should be n choose n? In other words, if we let k be n, what do you think it should be? Without any computing, how many ways are there to invite n friends from a list of n friends? Well, you're just inviting all of them. So how many ways I can invite all the friends? How many possible lists I have? Just one. Just one way. And it is true. If we put it in the formula will also show that. So here I'm putting k equal n, and I'm getting n factorial over n factorial times n minus n factorial, which is 0 factorial. And we remember that 0 factorial we set to be 1. So this gives me one way to do that. Similarly, what should n choose 0 be? Again, just think. We would like to not invite anyone for the party. How many ways we can do this? Well, there's only one way to do that. Only one invitation list, all empty. Just don't mail anything. Don't mail any invitations. It's going to be 1, and the formula shows that too. If we put k equals 0, that will give us n factorial over 0 factorial, n minus 0 factorial. And again, 0 factorial is 1. So we have 1. This example justifies why we agreed on this convention that 0 factorial be 1. It was not intuitive in the first place. This is to make such computations possible and meaningful. Let's practice with more examples. Example, an airline operates 7 daily flights from, let's say, from New York City to Los Angeles. Each flight can be late or on time. So every day's scenario of flights looks like this. The first flight could be, for example, late, and the second maybe on time, and the third is late, and then there are a couple flights after that on time, and then there's late and there's on time. 1, 2, 3, 4, 5, 6, 7. Yeah. So this is a scenario of one day, one possible scenario. Question: how many such scenarios are there in which, let's say, in which 3 flights are late and 4 flights are on time? In this case, 1, 2, 3 is late. So how many such scenarios are possible? To count all possible scenarios, we can just choose the late flights. How many ways are there to choose the 3 late flights? Well, there are 7 total flights. We would like to choose which ones are late. So there are 7 choose 3 ways to choose the late flights. Once the late flights are chosen, we're done. We don't have to select the flights that are on time, obviously, because they're determined by the late flights. Yeah, if I know which flights are late, if I choose them, then I automatically determine which flights are on time. This is the rest of them. So the answer is 7 choose 3, which is 35. An alternative solution would be to choose the flights that are on time, and there are 4 of them. So if I choose the flights that are on time, 7 choose 4 ways to do that, then the other flights will be automatically late, so I don't have to select that. So the number of possible scenarios is 7 choose 3, or alternatively 7 choose 4. If you compute that, it'll be the same number. As you can see here, there is a symmetry in this question. We could work with late flights, and the answer is going to be 7 choose 3, or we can work with on-time flights. The answer is 7 choose 4. There is kind of a symmetry going on here. Generally, if we have n flights, k of which are late and the others on time, we would get the symmetry property like this. N choose k, choosing the k late flights out of n, is the same as n choose n minus k, which is the number of ways to choose on-time flights. So this is always true. We actually proved it in a special case, but generally it's the same proof. What this formula shows is that the binomial coefficients are symmetric. Imagine what happens if I slide k from 0 toward n. First k is small and n minus k is large. Let's k is 0. And then as I slide it, this increases and this decreases, and at some point they meet. At what point do they meet is where k equals n minus k. That means 2k equals n. That means k equals n over 2. So for k equals n over 2, these numbers are the same. They meet. And that means that the binomial coefficients are symmetric about n over 2. Here is a picture, a graph, bar graph of the binomial coefficients. I plotted this, all the binomial coefficients n choose k for a fixed value of n, which is 20, and varying values of k. K could be anywhere between 0, 1, 2, 3, 4, all up to 20. And as you can see, the graph is symmetric about n over 2 here. The values of the binomial coefficients, as you can see, seem to follow a beautiful curve here. And it is not clear why at this point, but will become clear later. It is a normal curve, it's a bell-shaped curve. And why they follow that bell-shaped curve is explained by the central limit theorem, the major theorem in probability theory, which we will eventually get to in this class, but not now. Back to our example with the airline. Again, an airline operates 7 daily flights. Each flight can be late or on time. We would like to have 3 late and 4 on-time flights. What if we make an additional requirement that no late flights can be consecutive? That means, for instance, that if this flight is late, then the next flight may not be late. This scenario is a bad one. This is not allowed. We do not want to count that. Obviously, the number of such scenarios would be smaller. How many? How many such scenarios are possible? It's a trick question, and I will show you how to do that in a very cute way. First of all, let's line up the on-time flights, the 4 on-time flights. 1, 2, 3, and 4. We know that there are 4 on-time flights here. Now let's try to see where the late flights can be. Can be here, can be here, 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 or here. Each of these spaces may hold 1 late flight. Can it hold 2 late flights? Can it be like this? No. No late flights are consecutive. So each of these little spaces here can hold 1 late flight or no late flights. For instance, a situation like this is possible. Late, late, late. Let's write this down. So each space has room for at most 1, 0 or 1 late flight. And so how many scenarios are then possible? Each scenario is just a way to choose the 3 spaces and put the late flights in them. How many ways to do that? The ways to choose 3 spaces from, how many spaces do we have? 1, 2, 3, 4, 5. From 5 spaces. And that's 5 choose 3. And 5 choose 3, if you compute that, that's 10. So the answer is 10. And one more example. This one is related to a nice problem in algebra. How many solutions does an equation have? Let's say the equation x plus y equal 5 have. Let's require that the solutions be natural numbers. X and y could be numbers like 1, 2, 3, and so on. But not 1.5, or maybe not minus 10. For instance, 1 plus 4, x is 1 and y is 4 is a solution because they sum to 5. 2 plus 3, 2. 3 plus 2, we count this as a different solution. X is 3 and y is 2 now. And 4 plus 1. And that's it. And I think that's all. So there's 4 solutions. And that's the answer. But that was too easy. How about this? How about this equation? What about x plus y plus z equals, let's say, 6? How many natural solutions does this equation have? For instance, 2 plus 3 plus 1 is one of them. X is 2, y is 3, z is 1. Or maybe 1 plus 4 plus 1 is another solution, and so on. It would be hard to list them all, especially if we increase this number and we increase the number of variables here. It would be virtually impossible to list all the solutions and solve this equation and solve this problem in a simple way. So let's do this in a combinatorial way. Let's represent the solution in the following way. First of all, let's break 6 down into ones. 1, 2, 3, 4, 5, 6. That's a valid equation. And now let's represent, for example, this solution in the following way. Let's just group the 2 ones together, 3 ones together, and 1 1 together. like this. Group 2 of them like this, 3 like this, and 1 like this. So here x is 2, y is 3, and z is 1. We represented this particular solution to this equation. And we can represent any solution this way just by grouping the terms, grouping the ones. How many possible groupings are there? The grouping and the solution is determined by where we stop. We stopped at this plus and we stopped at this plus. These pluses are like milestones. They separate x from y from z. If we know where we stop, if we know these two pluses, then we know this determines the solution to the equation. Therefore, the number of solutions is the number of ways to choose two pluses from, how many pluses do we have? 1, 2, 3, 4, 5. From 5 pluses. And this is 5 choose 2. And 5 choose 2, if we compute that, is 10. So the answer is 10. Of course, you can solve now any problem like this, regardless of whether we have 6 here and how many parts we want this to be. We basically proved the following theorem, that any equation of this form, x plus y plus z plus t, let's call it like this, x1 plus x2, x k, maybe it has k variables, equals maybe n, any equation like this, has how many? Let's think. There are the pluses separate this. So how many pluses would we have? We had n minus 1 pluses generally, and we want to choose k minus 1 from them. So this is how many natural solutions we have. A beautiful theorem. We proved it in the partial case, but generally it's the same proof. Finally, one little remark. We counted this solution and this solution as different solutions. But suppose we want to count this as the same solution. Let's consider these two as the same solution. How many solutions are there now? In other words, how many ways are there to express 6 as a sum of 3 numbers, natural numbers? This equation, this problem, unfortunately doesn't have a closed form expression, and this is related. It's a deep problem. It's related to the notion of partition of a natural number n. There is no closed expression, but this is related to the deep area of combinatorics, where every partition can be represented by a Yann diagram. If you are interested in combinatorics, if you're interested in this problem, go and check it out. The partition function is the keyword, and the Yann diagram is a keyword. This is outside the scope of our course. Thank you, and have a good day.